I'd break chemistry down into three primary ideas: the idea of thermodynamics, energy changes; kinetics, which is reaction rates, how they happen; and then equilibrium, which is the balance between reactants and products. And everything else kind of fits under that umbrella, and even those three things overlap a bit. Today I want to take a look at kinetics, which is looking at reaction rates and reaction mechanisms. And if we're going to use those terms, we need to establish what is a reaction rate, what is a reaction mechanism. And I think there's few topics in chemistry that are like a global change to how you have to see chemistry, like kinetics, especially relating to reaction mechanisms. So let's talk about rates in general first. The idea of a rate is pretty straightforward, right? It's how something happens relative to time, right? And if we're going to talk about a reaction rate, it's what happens to a reaction over time. And specifically, we can measure that by looking at the amounts, right? There's the philosophical idea of what's changing. There's some change and how quickly does it take place. But we have to quantify that by looking at amounts, right? So we're going to have some change over time, which I think we would put into some type of change in amount over a change in time. All right? And for chemistry, it's a little difficult to get a change in amount, or at least it's harder, as opposed to like the macroscopic world. And an example I would use that my 8-year-old son was telling me was that rabbit populations double like every 4 weeks or something, he said, and this becomes some exponential growth problem. And in Australia, 24 rabbits were imported, and in 6 years there was like 22 million rabbits or something, or 22 million rabbits had been born. You can just count rabbits, this macroscopic scale, and it's pretty easy to keep a rate that way. And then they introduced something that killed off like 90% of the rabbits, and that improved conditions dramatically. Don't quote me on that story. But if we're looking at chemical reactions, we can't see the particles most often, but we can see the behavior, or the physical characteristics, or even the chemical characteristics of a group of particles. So if we're looking at some change in amounts, right? So typical things we might measure, we might have something like a change in volume, right? Or a change in pressure for a gas, all right? So if you're forming a gas, say you have like some decomposition of a metal carbonate or something, you can measure a pressure change, or you can have some constant pressure container where you're measuring a volume change, and that's pretty reasonable to do. With acids and bases things, you might get a change in pH, which is pretty directly measurable and not a big deal. You can do some colorimetry and maybe look at changes in color or color intensity, something like that. Maybe conductivity, a change in conductivity. For exothermic or endothermic reactions, you could have some change in temperature. And then I think one that at first seems the most evident, which would be a change in mass, right? Which actually ends up being a bit harder because you have to have some heterogeneous system, right? You got to have different states of matter there, so you have to have some heterogeneous. So for instance, like the change in volume or pressure, you might say, with a decomposition reaction of a calcium carbonate, for instance, you could measure a mass change of the solid as it was heated and it was releasing that gas. That wouldn't be a big deal. Or you could theoretically come up with some way to measure of the mass of a precipitate that was coming out of a solution. But if you've got some situation like maybe a single replacement reaction with aluminum and iron oxide, like the thermite reaction, you have a solid and it's turning into a solid and a solid, and by conservation of mass, you might not know the rate there. It's a pretty quick rate. So the idea of reaction rates, how quickly something's taking place, we're just looking at how things are changing with time. With reaction mechanisms, that's a pretty interesting idea, because it changes fundamentally the way we look at chemical reactions. And I want to take a side note here and look at an energy diagram where we're talking about reaction coordinates, they say, right? Versus another name, they might call it reaction progress. And on one side, we've got energy over here. So it's how energy changes with time for different reactions. And what we're looking at is where reactants start out. So you have all reactants there. And then we have some energy barrier, our activation energy, and that goes down, and you may have an exothermic reaction where you have your products. And when you talk about thermodynamics, you've got a difference between reactants and products. In fact, I'm going to label some of this stuff right now. So this distance right here, you might say, is a change in enthalpy, a delta H, right? And your distance from here to here, we would say, is an activation energy, EA, all right? And we could have a reverse activation energy from there to there, and many other things. Now, the key idea here with kinetics, and as we relate it to thermodynamics, is the difference between where you start and where you end up, and how you get there. So thermodynamics deals with state functions generally, like enthalpy and entropy and Gibbs free energy, where all that matters is where you start and where you end up. It doesn't matter how you get there. And I'll talk about an analogy for that in a minute. So the realm of thermodynamics ignores this. It looks at where you start and where you end up. The realm of kinetics looks at this right here, right? So we have kinetics that is exclusively determined by how you get from reactants to products. And that makes sense. And then we've got thermodynamics here and here. And let's take a look at an analogy that I use with my classes. We'll say that I used to live very, very close to the school, relatively speaking. So we'll just say my house was right here, and then there were some train tracks right there, and the school was right there. And I lived about maybe 3/4 of a mile as the crow flies, as we say, right? But I couldn't go that way because that's not where the roads were. I either had to go out to the road and go over, and then go over and then drop in, or I could go this way and go over and over and over and come in. And this was about 2.1 miles, and this was about 1.7 miles, and this was about 0.75 miles. And looking at this example, or looking at physics, you've got the idea of displacement, how far apart two things are relative to each other. In this case, my displacement is 0.75 miles, and that's independent of how I get there. The distance from here to here is independent of how I get there, and we call that a state function, something that is path independent. Whereas the route or the pathway is completely dependent on how I get there. So the amount of time it takes might be completely dependent on how I get there. And sometimes after work, 1.7 miles might take like 20 minutes due to a great traffic flow design. So anyway, kinetics, completely path dependent, not dealing with state functions. Thermodynamics, pretty much exclusively dealing with state functions, difference between where you start and where you end up. So the way that comes into play is with reaction mechanisms. It's not where you start and where you end up, it's how you get there, all right? And so the mechanism is a series of steps by which a reaction takes place. And I guess I'll write that down. Reaction mechanism, this series of steps by which a reaction takes place. All right? And I think that's where our idea of chemistry has to change to accept kinetics. So if we look at a simple reaction, right, like some synthesis H2 and Cl2 goes to HCl, all right? If you ask someone, and I guess we need to throw a 2 in there, if you ask someone, like, what happens? And I think that we look at it as an absolute system where it's like this and this turn into this. But there are things going on in between. So like, if we were to picture it, if we had to draw out some picture, we might say I've got like a hydrogen, and I'm going to put them with a chlorine and a chlorine. So one diatomic chlorine, one diatomic hydrogen, and then this turns into hydrogen now bonded to the chlorine, and hydrogen now bonded to the chlorine. And whatever magic happened along the way. But the reality is there might be better ways to get things done. If this were a possibility, where you maybe have this in some high energy transition state or some other activated complex, it's pretty improbable though. So we're going to look at this idea and see what can actually happen, and I'm going to try and write out a mechanism for it, a series of steps, or at least a sample mechanism, and I'm going to try to tie it in with a picture. So we'll see how this goes. So let's look at the pieces we have, and we'll start with that. I'm just going to pretend here that I have a container with some hydrogens, and I want to be somewhat careful here. I'll just go with the actual letters. and some chlorines. And we'll put a couple of those in there. It doesn't really matter, but so are those two hydrogens or whatever, is a hydrogen molecule and a chlorine molecule going to bump into each other? It's possible, but there may be a better way for things to happen. So as you look at the bond energy and things like this for these compounds, it turns out the chlorine happens to have a pretty low bond energy and something like ultraviolet radiation. So I'm just going to put that right there to symbolize like ultraviolet radiation energy from outside here. It'll break that chlorine-chlorine bond, and it'll give you 2 chlorine-free radicals, all right? And I'll just put those other dots in there and then promptly erase them because it's going to be too much work. And you can take note that this notation is just going to show that I have 2 chlorine-free radicals. What's special about these free radicals is that they're really high energy and they're very reactive. So it's totally feasible to say maybe one of these chlorine-free radicals can bump into one of our hydrogen molecules, right? And now we have a hydrogen bonded to a chlorine, and we have a hydrogen-free radical now, right? It's like some Newton's cradle situation where one side hits and knocks another one off the other side. High energy species hits this, and we get this reaction, and it breaks into those 2 pieces there. And so, like, let's look at how that might be here. First step, you've got this chlorine that spontaneously decomposes, right, in some electromagnetic radiation or whatever, right? And then it hits this, so this chlorine bumps into this and forms a bond here, and then this breaks off, and now you have that hydrogen right there, right? And we've used up one of these chlorine-free radicals there. And I think visually, it's very clear what could happen next, or a possible scenario, right? In fact, this hydrogen and this chlorine could bond together. So I've got another chlorine-free radical, and I could just say, oh, well, I've got my hydrogen-free radical and my chlorine-free radical, and that could give me HCl. All right? And at that point, we've got HCl, and then our H got used up, and our Cl got used up, and we'd be done, right? And there's a name for that type of step. Alternately, if you look at the picture here, instead of this colliding here, this could have collided right there. And we could have a scenario where maybe that hydrogen-free radical bumps into a chlorine molecule. And it's the same Newton's cradle type of scenario where this hydrogen bumps into this. It has enough energy for that bond to fall off, and then we have a chlorine-free radical again. So we might have our HCl and a chlorine-free radical again. And I'm going to skip some of those dots to save time there. So we've got the scenario, chlorine breaks apart. Think about this, by the way. If this chlorine-free radical up here hadn't bonded with this hydrogen when this broke apart, there's also the probability that this could bump into that and form that bond again, right? Or once we have a hydrogen-free radical, that could bump into 2 hydrogen-free radicals. So we might have Cl free radical and then the chlorine-free radical giving you that chlorine back, right? Or a hydrogen-free radical and a hydrogen-free radical bumping together to give you that scenario there. So we've got a few different possibilities here. This started the reaction. We've got a name for that. This allows the reaction to continue, and we've got a name for that. This ends the reaction. This isn't going to continue past that. This has a continuation possibility. This is going to end it, and this is going to end it. So let's talk about the terminology for these things. I think that like these steps, these little pieces are more feasible than like this bumping into this and like just bonds falling apart for no apparent reason. There's got to be energy involved, this bond energy required to break it, and there's better ways to get there than others. So let's look at some of our terminology here. Since this step starts everything, its name is unsurprisingly a chain initiating step. All right, and so you've got a few options here, which you can start, you can stop, or you can keep it going, right? Those are your 3 possibilities. That one starts the reaction, okay? There are some things here that can end the reaction, like this makes a compound. It doesn't make something that's going to keep going. And right, this could break down into free radicals. Any of these can go in either direction, technically. So this reaction, when it happens, produces something that would allow the reaction to keep going, right? To propagate. So this is a chain propagating step. And each of these we would call an elementary step in this mechanism. This one here ends things, so it would be a chain terminating step, right? And if we follow through, this one would be propagating, and this one here would be terminating. And again, just so we get everything labeled appropriately, these are all elementary mechanism steps. All right, the pieces of the reaction as we go along. So our two main ideas here as we begin kinetics, we've got rates, and we can measure those rates by looking at concentrations or other things. We've got, and those rates actually are going to depend on the particles we have and all these other things, and we're going to have mathematical rate laws to figure that out. And then we've got mechanisms, how we get from reactants to products. And we're not so much worried about where the reactants start in terms of energy and where the products end up in terms of energy. We're worried about how we get there, the pathway. So we're not looking at state functions anymore. And so after this, we're going to have to take a look at the idea of like what I was saying, which is like things are colliding, and we'll tie that in with collision theory.